Hello, hello. Testing. Hey, everyone. Cool. Yeah, thanks for coming. Excited to be here presenting blobs in the future of the blob mempool. And this work was joint with Julian and Francesco at the Ethereum Foundation. So just to set the stage a little bit, I'll kind of outline what the agenda of the talk is. We're going to start by talking about blob services. And I think it's important to kind of ground our discussion in what do blobs do for L2 users and for the rollups themselves who are consuming the blobs when they post to Ethereum. And kind of once we've grounded the discussion in what blobs are for and kind of what the main point of them is, we'll go through how blob gossip and validation works on Ethereum today. And this is important because this is kind of the two modalities in which people have to download blob data. And it's kind of good to understand how it works today before jumping into what changes with PeerDAS. And PeerDAS is kind of one of the next upgrades to the Ethereum protocol, and it aims to kind of scale the amount of data that Ethereum can handle, and we'll kind of go through how that works and why. And then we'll talk about what we can do moving forward. And in particular, we'll talk about how PeerDAS introduces this kind of asymmetry between how blobs are processed in two different parts of the stack. And I'll outline some of the things that I think are important moving forward. So yeah, just to start with blob services, I think it's helpful to kind of think of them in terms of confirmation rules. And I informally define a confirmation rule as a signal indicating the status of a transaction. So this can mean a couple things. One of the kind of default ones is when your transaction on Ethereum L1 is actually included in a block, right? And Etherscan reflects this by saying this block is unfinalized and may be susceptible to reorgs, but it also gives you that success green check mark that means it was included in an Ethereum block, right? But that's not the only confirmation rule you get. Or the only confirmation you get, rather. You also get the finality, which is a much stronger guarantee. This is something that everyone's probably very familiar with, which is the block is finalized and cannot be reverted without slashing at least 1/3 of validator stake. So this is kind of the second much stronger confirmation that L1 transactions get. But L2 transaction also get confirmations, right? So this is a picture from Basescan, and we can see that it has the green check mark. It says success. This transaction has been sequenced and executed. But the confirmation is actually coming from the sequencer itself, right? And this is kind of one way that people get assurances about their L2 transactions. And the takeaway from this slide is that blobs actually provide confirmations for L2 transactions. But the type of confirmation and the importance of that confirmation to the user depends a lot on the sequencing model of the L2 itself. So I'm going to walk through two different versions of sequencing for L2s and show how that kind of results in very different blobs, in particular blobs that have very different time preferences for when they need to land on the L1. So as I described in the previous slide, let's start with like the centralized sequenced L2. This is kind of the dominant model of rollups that exist today. And we have a user that sends their L2 transaction to the centralized sequencer, and they get this confirmation number 1 from the sequencer, right? And this is kind of the green check mark I was showing in the previous slide, but for most people, this confirmation is sufficient. Like, I trust Coinbase to sequence my transaction fairly, whatever, and I trust that they're not going to renege on that promise, that it was executed in the order that it was confirmed to me. But of course, this isn't the end of the life cycle of the L2 transaction, because all I have right now is kind of a trust me bro handshake from the sequencer. There's also the process of getting that L2 transaction data posted to the L1. This is kind of like the whole point of rollups in the first place, is so that transaction data makes its way to the base layer and kind of inherits, in some sense, the security of the L1. So the kind of dominant way that centralized sequencers land these blobs with L2 transaction data on the L1 is by sending them to the public mempool. And once they're in the public mempool, they get picked up either by a builder or a proposer, who then includes it in an Ethereum L1 block. So you kind of have this nesting where the L2 transaction gets packaged into a blob, and that gets packaged into a block. And that block is sent over the consensus layer network. And this is actually another confirmation, right? So the confirmation now is that, oh, I actually see my L2 transaction data posted to Ethereum. But of course, the second confirmation isn't that important, and the takeaway is that the first confirmation is actually sufficient for most users. And there's kind of no urgency for the centralized sequencer to actually land the blob on the L1. And for this reason, I call these blob transactions patient, right? And in particular, they're maybe happy to go through the public mempool so long as they get included within a slot or two. And they're not worried about kind of getting front ran. They don't carry MEV. They don't need to play timing games and stuff like that. So on the opposite side of the spectrum, there's a set of blob services that actually do lead to a very different paradigm for blobs. And in particular, that is the sequencing model of total anarchy. And in total anarchy, we basically say, okay, anyone who sufficiently lands a blob on the L1 with some L2 transactions is the L2 sequencer for that slot. So everyone's kind of competing, racing to get an L1 transaction or an L1 blob transaction landed with all the L2 transaction data in it. So I use Tycho as the example here because they're the first roll-up to kind of try this and play around with this experiment. But basically, once the L2 transaction gets sent to the Tycho public mempool, now you have a slightly different set of actors who are searchers on the L2 who are looking at this transaction and trying to sequence it, right? So there might be MEV they can capture, there might be transaction fees that get paid to them for including this L2 transaction in an L1 blob, but that's kind of how the process is playing out. And in particular, those searchers are sending blobs with the L2 transactions sequenced to the L1 builder or proposer. And from there, the flow is the exact same, but now this confirmation is the first confirmation that the user has received, right? So they didn't get that green check mark from the centralized sequencer. The only time they have any confirmation about the L2 transaction being sequenced and being executed is when they see it in an L1 block. So this is a very different paradigm, and it leads to what I call urgency or like impatience for the blobs, because now there's a competition. Everyone's racing to be the first person to land a blob on chain, and this kind of results in some sort of MEV in the L2 space playing out on the blob market. So kind of to summarize these two discussions, there's kind of two different paradigms for which blobs can be posted. There's kind of the public patient blobs that are happy to sit in the public mempool, and then there's these private blobs. I guess, one other point I wanted to make on this slide is that the searchers in the number 2 label there are sending their blobs directly to the Ethereum builder and proposer. They're not going to the public mempool. And the reason for that is because they're worried about someone else listening to the mempool and potentially kind of like rugging them, going in front of them, or unbundling some of the transactions that they sequenced. So this plot here shows the percentage of private versus public order flow. I guess it just shows private, and it's a little hard to see, but on the blue shows the percentage of blob carrying transactions that are private order flow, and we see it's about 20%. And the orange shows the share of blobs that are going through private channels, and that's about 7%. So I guess the takeaway here is that actually most blobs go through the public mempool, and I think the explanation that makes the most sense to me is that the blobs are patient generally and coming from these centralized sequencers, and thus don't need the type of guarantees that going through private channels would provide to them. And I guess this is important to understand because when we think about designing the protocol to scale blobs, it's useful to think about how these blobs are actually flowing through the network, and that helps inform the protocol design. So the TLDR here is we expect patient blobs to be content using the public mempool as long as it provides a relatively good inclusion service. And relatively good is kind of intentionally vague, but it might mean that if I post a blob to the public mempool, it gets included within like 2 or 3 Ethereum blocks. And for most rollups who are doing like this batching process, they get a bunch of L2 transactions, they construct the blob, they send it to the blob pool, and it gets included. That's like probably enough time or like a sufficiently good service for them versus someone who's actually like competing and needs it landed that slot. The public blob pool probably will not offer that service for them. And I guess to kind of not bury the lead here, I believe that blobs distributed through the public mempool are probably better for both builders and for low resource attesters. So I'll kind of try and justify that claim. But the takeaway here is that I think we should strive to maintain the public mempool for blobs to be the dominant way that they go through like basically land on the L1. Cool. So now we're going to talk about that actual process. So there's kind of 2 ways that blobs there's 2 kind of roles that validators need to perform to validate blobs. The first note here is that Ethereum nodes run both execution and consensus layer clients, and actually both of these clients are connecting to different peer-to-peer networks. So there's different peers. This is a different way you can source blobs, either from the consensus side or from the execution side. And the blob mempool, which I sometimes refer to as the blob pool, is an execution layer object. And just like the normal mempool, it maintains a set of pending but not yet included transactions, right? Of course, these are blob transactions, so the way it handles them is slightly different because they're 128 kilobytes, but generally speaking, it's just this set that everyone maintains in their local node's view. The block validation in a testing flow is a consensus layer operation, and it checks for availability of the blob data, right? So the way this works today is there can be, like, let's say there's 6 blobs included in an Ethereum block. In order to check that the block is valid, you also have to download those 6 full blobs and confirm that they're available and have fee-paying transactions behind them in order to confirm that the whole block is valid. So attesters who are voting on the block and deciding which fork they view as the head of the chain will kind of need to download all that data in order to make that decision. Right. So how does this play out kind of in time? So I have like this 2-slot diagram here to try and help visualize, and we have 4 public blobs, which are these green blobs on the left, and then the 2 private blobs are the purple on the right. And the important thing to note here is that since the public blobs aren't depending on kind of being released just in time as the builder publishes the block, they're able to kind of be spread out and amortized over the entire previous slot. And once the block actually gets published, any blobs that haven't been seen in the mempool need to get gossiped before the attestation deadline. So if I'm an attester and I see this red block and it has all 6 of these blobs, if I've seen the 4 public blobs beforehand, all I need to download before the attestation deadline is the 2 private blobs that were referenced by the block. And the important note here is that blob pool blobs can be used for block validation, right? So there's this kind of coupling between the two, where if the blob pool is providing me a good view of the set of blobs that were being gossiped around, I can use those to validate blocks on the consensus layer. So it's kind of like this nice synergy between the two. And the reason for that is fundamentally because the DA check actually needs to download the full blob data, right? So there's kind of no getting around it. You have to see the entire contents of the block before attesting to it, and that's why the two are working together well now. But as might be kind of clear from the direction I'm going here, this doesn't actually stay the same with PeerDAS. And let's just like remind ourselves what PeerDAS is. PeerDAS is slated to be the headliner EIP of the Fusaka hard fork. And it's aiming to massively scale the blob count by reducing the DA check to a subset of the columns of each blob. So right now, blobs are these kind of commitments to arbitrary, or they're commitments, and they come in these terms of these 128 kilobyte kind of data format. And post PeerDAS, you kind of break up this blob vertically and only need to check that a subset of the columns for each blob are available to confirm the block. So how does that look? EIP 4844 downloads kind of all of the green space there, kind of represented by this diagram. But on the right, PeerDAS says, okay, we have many, many more blobs, but you only take a slice of the blob, and that's what you have to download to check the availability. And the reason this works is basically everyone gets assigned different columns, and if everyone attests that their columns are available together as a whole, the network confirms the availability of the full set of data. So this is what PeerDAS is aiming to do. And now let's look back at our slot diagram and see, okay, what's actually playing out here. So now in the first slot, in slot N, we have these public blobs, but now there's many, many, many more of them, right? And because we increased the number of blobs that happen per slot, all of these blobs could get gossiped through the public mempool. But when the slot actually begins and the block is published, the purple represents the private blobs from before, but now we only need like small columns of each of the private blobs that were downloaded to confirm that the block is valid. So the key observation here is that the types now mismatch, right? So on the left, we have public blobs going through the public mempool, and that's the entire 128 kilobyte object. And on the right, it's just a column. And this is kind of what leads to this asymmetry between what the execution layer is providing and what the consensus layer actually needs to download to attest to a block. And basically, the summary here is without changing anything, the blob bandwidth increases by 8x, while the DA check remains constant in terms of bandwidth consumption. So we kind of threw the baby out with the bathwater a little bit. We said, okay, we're going to only subsample parts of these blobs on the consensus layer, but on the execution layer, if you want to stay connected to the mempool, you're going to have to download the full blob data. So this is kind of where that core tension's arising from. And yeah, I guess now we can zoom out a bit and say, okay, do we actually want to do anything to address this asymmetry? And the first point is that no protocol enshrined changes will be implemented for the blob pool in Fusaka, right? Like Fusaka is already set, the scope of the hard fork is committed to, and it's not going to change this asymmetry. So this asymmetry will exist at least for one hard fork, kind of no matter what. The second fact is that the number of validators self-building, so constructing their own blocks, is so low that the blob inclusion service might not significantly degrade. So what I'm saying here is that like maybe that asymmetry doesn't matter if we trust that the 95% of blocks being built by builders can contain up to the 48 blocks, then for rollups who are happy sending their blobs through the public blob pool, this service remains sufficiently good. Thirdly, there is not an, cool, 5 minutes. There's not an obvious reason we will shift to a private blob only regime. And that's exactly for the reason I started at the beginning with, which is centrally sequenced blobs are happy to go through the public blob pool. Like there's no economic forces pushing them to private channels because there's no MEV available in these blobs. And that leads to claim 1, which is that we should probably keep the blob pool around to amortize the blob bandwidth consumption for low resource attesters. So that's my first claim. And then the second claim is solving the fundamental asymmetry of blob validation and gossip is important to continue the scaling roadmap, right? So PeerDAS may be fine, like the blob pool will only consume maybe 10x the resources that it consumes now, but once we go to 2D sampling, it gets another order of magnitude increase. And it just like, it doesn't make sense to say, oh, the execution layer is continuing to scale linearly in the number of blobs, but the consensus layer is only scaling kind of sublinearly. Like that feels directly at odds to me. So, right, one straw man proposal is what can we do? What if we just shard the blobs that we sent to the blob pool, right? We're saying we vertically shard the consensus layer DA check. Why can't we just shard the gossip itself? And the reason we can't do that is because this provides a free DOS vector on the blob pool. And the reason for this is previously the mempool can check that any transaction that gets gossiped is fee paying and comes from like, is a valid transaction basically. So in some sense, the people who are sending those transactions are paying some economic weight behind the transaction that they're sending, and thus they can't just like spam arbitrary bytes into the mempool. But if you just subsampled a blob into columns and gossip those columns directly, there's no way to like formally prove that that column belongs to a fee-paying transaction on the blob. So that's one problem. And the kind of key thing here is that we need to ensure that columns that are gossiped pay for the service that they consume, or the resources that they consume. Like that bandwidth has to be paid for by someone. So what is one idea for what we could do moving forward? I like to call this the blob pool ticket auction with refunds, which is kind of a mouthful. But the idea is, okay, we have this scarce resource we want to allocate. Why don't we run an auction, right? And we can auction off not blobs themselves, but access to the blob mempool. And you could simply do this kind of in protocol with something like this, where you, a few slots before, have bids submitted as L1 transactions, and the bids are processed and kind of consumed that way. But what this allows us to do is say, when a blob gets gossiped, we only verify that it comes along with a winning ticket from that auction. And now we know that whoever has, whoever does the gossip itself has like already paid for that access. And importantly, we also include this refund thing because we want write access to the blob pool to be free in expectation. Because right now it's free, right? And if the blob itself also lands on chain, then it did end up paying a fee to the protocol. So we can probably refund the access that they paid for to the mempool. So again, this is a little complicated. This is just one design. There's like a ton of kind of optionality here, but I think it's worth considering at least a little bit. I'm gonna skip this slide just for the sake of time, but I'll post the slides later and happy to discuss more after. But I think there's a few questions that are worth highlighting just for the key stakeholders or the constituents of blobs and this whole blob pipeline. So there's questions for rollup teams, like how do you think about public versus private blobs? How much latency are you okay with for landing blobs on chain? And would you participate in the blob pool auction? Then you have the builders who are actually the ones creating the L1 blocks, and we could ask them, how much do you depend on the public blob pool when deciding which blobs to include? And what guarantees do you offer to private blobs? And then for staking operators and people actually doing the attesting to blobs, we can ask how they plan to handle the bandwidth increase resulting from larger number of blobs, and would they continue downloading blobs in either of the sharding worlds that we discussed. So I'll wrap here. These two links at the bottom are articles that kind of should help fill in some of the details from this talk, but thank you very much for your time and attention. Sure, yeah, if there's any questions, happy to. Seems like no. Cool. All right, thanks everyone.